My first major project was a game called Prototype, and before it was greenlit, we had to produce a vertical slice of gameplay in about 3 months. Performance quickly became the biggest issue. Nobody had any idea how to get it from a couple FPS up to a showable 30. And so I got a trial by fire introduction to optimization, and continued in that role afterwards and on other projects later in my career. Optimization is an incredibly deep subject, as I quickly found out, and there are so many ways to approach it. I don't claim to be an expert, but I've been lucky enough to have gotten opportunities to play a lot with the subject. Let's start with a common and vague problem, intentionally. Let's draw a whole whack of trees in the scene, so here we go, they're coming in, and as they come in, oh look, the frame rate is dropping. Let's pretend you know nothing, like I did. How do you make this faster? Because you know very well that games do render jillions of trees, among other things, quite successfully. So it's absolutely possible we're just doing something seriously wrong here. Often it starts with a couple simple questions. How fast does this need to be, and on what? What's your target frame rate? You going for 30 FPS on a low-end phone? 120 FPS on a PS5? In essence, what's your budget? This is 1 second, and so if you're running at 60 FPS, then it means that this little bar here, 16 2/3 milliseconds, this is what you get to render your scene. At a studio, you'd have to divide this time obviously with other things that want part of that time too, because I assume your entire game isn't just about drawing trees. So you have to share your frame budget, both CPU and GPU, with other stuff. In this little frame breakdown study on the graphics of Doom Eternal, you can see that a lot of things go into drawing a frame. You've got your GPU skinning to animate characters. There's also shadow mapping, they've got a depth prepass, high Z, screen space ambient occlusion, particles, post effects, UI, whatever. There's a bunch of stuff in here. You don't have to understand it all. But during development, these would absolutely have budgets on the target hardware, how much frame time they can have in order to hit the target frame rate. Now we need to start our investigation. Manually taking timings can get you surprisingly far, or better yet, some sort of tool to examine performance, a profiler. Depending on what you're profiling, let's oversimplify and restrict ourselves to CPU or GPU problems, then you'll need a way of getting information about slowdowns. Some common choices would include tools by Intel, AMD, or NVIDIA, stuff like VTune, uProf, or Insight. I found a nice little list here on this Rust profiling page by Nicholas Nethercoat, who did a lot of the work with the Rust compiler performance for Firefox. We'll do some top-down analysis. If you're doing profiling, it'll generally look like this. That is, starting from the top, here's where we update all the things. That breaks up into smaller chunks where we update the foos, and then we update the blah, and we'll try to see where all the time is being spent. You can see why this is called top-down analysis, because you can drill down further and figure out where your overall time is being spent. Bottom up, by contrast, we'll look again at the frame, but we'll look at functions being used everywhere, like this matrix update, and by making those fast, you make everything fast. This is great for finding those functions where you really want to squeeze more performance out of them. In our actual case, let's figure out what's wrong. So, in the top left, I've got the frame timings running, both the CPU and GPU time, because this problem can potentially span both. We can see the CPU sucks more than the GPU, so let's use a profiler to see why. So we fire up a profiler of some sort. They all look different, but present similar information. Because I'm a lazy man, we're using JavaScript and Chrome's DevTool profiler, but it'll present a breakdown, similar to others. So we can see from this breakdown, we're spending, well, all of the time on the CPU on draw commands, which isn't exactly a surprise. We're not even drawing that many. So we want to make this faster. How do we do that? The general steps to fix any performance problem look something like this. You establish your budget. That's already done. We're dedicating our whole frame to trees. So the next steps would be, well, we'll fix this problem, make it nice and small, and then, if performance still sucks, we loop around and figure out what the next biggest issue is. Let's start with a really simple example. You've got this function here, really slow, and your profiler is telling you this thing is a problem. What's your first move? I mean, we could take a look at it, and maybe we'll get really lucky and there's a bunch of really, really stupid things going on in there. Remove those, and voila, some of our easiest performance problems are solved. If we take our tree example, well, maybe someone intentionally wrote this super poorly for YouTube video reasons. Now we can share materials, share underlying geometries. Those begin to give you some modest gains. We've bumped up our number of trees for the same frame rate. Looks like we're hitting about 7 to 800 in this nonsense example. Even better is using GPU instancing. That's essentially telling the GPU we're going to draw the same tree a whole bunch of times. Go do it. That gets us up to 30,000-ish trees. We're also spending almost no time on the CPU now, so we're probably bottlenecked on the GPU. Once that absurdly low-hanging fruit is out of the way, now what? Well, let's back up a bit and think about things in terms of what does your system, the one you're optimizing, what does it look like? At its core, stuff goes in. These are your inputs to the system. You process them in some way, and then stuff goes out. The question is then, what parts of this process do you control? Because changes to this processing step here, they're at the mercy of your input. So if you control the input, it can be much more lucrative to start there instead. When you're going to change the input, often it's productive to think about, well, what does my hardware even want? What shape should the input take to maximize hardware utilization? In general, hardware likes a few things. This is a sweeping generalization, but it likes giant contiguous chunks of memory, and it likes predictability. Let's say we're talking about the CPU, and we're doing work with things in memory. If you process things in a contiguous chunk of memory, you process this chunk here, then afterwards you process this chunk here, and then this one here. Well, the CPU can boldly predict that you'll need this chunk here, and just have it ready to roll when you move on to process your next chunk. Crazy, eh? But if you're randomly bouncing around memory looking for bits and pieces, the CPU has no goddamn idea where you're going to look next, and so eat a big fat cache miss. Random access memory can be accessed randomly, but really shouldn't be. Cache misses are a big deal. If you're not sure what they are, this little box here, let's say this is the time that it takes for the CPU to execute a simple instruction. Now let's say that you want to do something that needs to grab something from memory. Then if it lucks out and that thing is in the L1 cache, it takes about this long, in relative terms. But L1 caches are small, so if it's not there, often the CPU's next option is to check L2, which takes a bit longer, but not crazy long. Miss that though, and now you're reaching out to L3, and the cost of doing this is steadily rising. After that, if the data you're looking for isn't in any of the caches, or in other words, this is a cache miss, then you're reaching out to main memory, which takes roughly forever in computer terms. This is why cache misses hurt so much. So if you lay out your data in a way that the CPU can predict what you're going to need next, you may eat a lot less of these. And your CPU can even try to predict which way your code is going to execute. If we compare these two loops, they're identical for the most part. So this branch here on the left, predicated on data in a random order, there's no stable pattern for the CPU to pick up on. And so it's going to do so much worse than this one here. Even though the code itself is the same, the data is in a predictable pattern. Or, since you control your inputs, you could simply separate them out into separate lists. Job done. The differences here are subtle and easy to miss. If you imagine your CPU like a little machine in a factory, you've got your program's commands coming in as a little assembly line and the results coming out as a little assembly line. Inside, though, it doesn't necessarily have to be done in this order. Imagine the CPU is looking at these boxes, and you can see that this box here depends on this box here. And this box here, it wants something from memory. Reading from memory takes forever in CPU terms. So this whole factory operation is now blocked. The CPU wants to keep going, so maybe stuff gets shuffled a bit. We can execute this box here while we wait for the other one. Everything still comes out in the right order. Let's reset things a bit. Now imagine this box is a branch. So you got your if, then, else. Let's just give these different colors so you can see them clearly. Again, the CPU doesn't want to slow down, right? Figuring out this if will take a bit of time. So while it waits to see which way it should go, it actually just tries to guess and keeps going. If they're right, awesome. If they're wrong though, they have to backtrack and start again. It's a fantastic optimization, but mispredictions are a problem. Among other things. There's so much to learn here, it's not realistic to do more than just put these on your radar, but now that you're aware, there will be links in the description, or I'll make more videos about it later. So back to that big question from earlier, what shape should my data take? So your function here, it could be a game update loop. It could be a lot of things. Here it processes a bunch of world objects, which are in some random order. So we iterate, grab the entity from the world object, and do our little update. From a performance standpoint, you've got pointer indirections, you've got virtual function calls, which means potential for a lot of cache misses and branch mispredictions. With some minor changes to the input, the performance of the function can substantially increase. When you're more mindful of data layouts, like in this example here, we can burn through updates way faster by packing them all into contiguous blocks of memory with no lookups. Now your CPU has one giant workload to burn through. The really cool thing here is that since your data is all tucked away nicely in a big predictable array, it gets a lot easier for either you or the compiler to vectorize this. Many CPUs have the ability to do SiMD, or single instruction multiple data, meaning you can now process 4 or 8 or even more things at once, instead of one by one. The basic idea, though, is do your stupid things offline if possible. Once your data is in order, then you can get your code in order. Here's a few good places to start learning about this. And as a quick aside, if you've ever wondered why ECS frameworks have emerged so strongly in recent years, it should make a lot more sense now. They're in essence a data-first approach. So in our tree example, we can take our tree and optimize it, weld together redundant vertices, that'll reduce the workload. We'll reorder the mesh to maximize vertex cache usage. We'll quantize the data because you don't need these big bloated vertices. You can crunch them down quite a bit. There are a zillion tricks in this space. Octahedron mapping for your normals. An entire tangent space can be compressed to 4 bytes. Positions can be done with half floats or, much better, 16-bit integers with scale and offset. UVs can be similarly quantized in many cases. And finally, we can compress the textures using a GPU compressed format. These might sound unimportant, but smaller vertices and textures mean better use of bandwidth and more crap fits in the cache, meaning more trees before you hit the GPU's limits. Look at our forest, it's getting bigger. You can see in this shot we've hit over 50,000 trees. So the scene is growing quite a bit. One interesting question arises the first time you start doing these optimizations. How fast can this really go? The first couple of wins are great. The next few will probably be smaller and diminishing returns after that. Sometimes it's helpful to know what the speed of light is. Or in other words, if everything was perfect, how fast could this really go? Because you're not going to go faster than that. And as you approach that limit, the amount of time versus the amount of gain you make will really start not being worth it. So what are your other options? Do it smarter. Or said another way, don't do the things you were going to do but didn't have to. That one isn't quite as catchy. There's really nothing faster than literally just not doing it. So the first approach we talked about, we did the same work, we just made it faster to do that work. This asks the question, is there a way to literally produce the same effective output, but do less overall work to get there? Can we get the same result while doing less work overall? If you're walking from A to B, well, you can get there faster by just doing an all-out sprint. That's doing the same work, just faster. Or you could find shortcuts. Take a little shortcut through the mall, fly over the mountain, whatever. Same destination, but you're shortening the overall route. This tends to be extremely domain specific. So let's look at our trees, but let's look at the scene from above. If we highlight this area here, it's called the view frustum. It corresponds exactly to what you can see on screen. So these highlighted trees here, they're visible, while the rest of these are out of view, so they contribute nothing visually to the output. But in our naive setup, they still get sent to the GPU and take up processing time. So don't draw these. Simple. Cull them. Bam. Instant win. You've raised the ceiling by quite a bit. How does the speed of light factor in here? Previously, it was the maximum speed that you could do certain operations, like, say, draw trees. That hasn't really changed. If I had a theoretical max of 100 trees before, that still applies. But the difference is now, they're the ones on screen, and the off-screen ones don't count anymore. The ceiling still exists, but now you could have 1,000 trees in the world, because only 100 would be on screen at any given time. There's more avenues to explore here. In the case of our trees, we could use some sort of spatial division to rapidly discard larger portions of the world before fine-grained checking each tree, or take another approach. Obviously, some geological features may obstruct our view, and hence anything behind that would be occluded. Watch my video on occlusion techniques to understand how much effort goes in here. But let's say that you somehow get perfect information. You're able to, in the blink of an eye, get a list of every single visible, non-occluded tree. Well, you're still bound to your speed of light restriction, unfortunately. The question then becomes, how do you break the speed of light barrier? Well, anybody who's been in a grocery store in the last couple of years knows, how do you make more money without providing a better product? You don't. You cheat, shamelessly, and hope either nobody notices or cares enough to complain. Voila, profit. There's some really great examples over the years of games using tricks to get away with things. The fog in Silent Hill obscured your view and provided a lot of atmosphere, and also ensured devs didn't have to draw too far. The infuriatingly long elevator scenes in Mass Effect gave the team time to banter, let you get to know them better, and provided cover while they loaded the scene. And Jack and Daxter's streaming system would, apparently, have you trip and fall when you outran the game's ability to stream in assets. That's not from any official docs, but other games have apparently done the same thing. Let's turn our attention to these trees. Here's our tree up close in all of its glory. And here it is far away, I guess, not in its glory. Well, since it's far away, why even bother drawing a good version of it? We could substitute a lesser quality version and maybe nobody will notice or care. Maybe I already did. It's so far away. Or maybe I'm lying. Can you really tell? This is great for a variety of reasons, which this brilliant YouTuber dives into in his video on why LODs, or level of detail, why those work so well. Beyond the savings for the smaller simplified mesh, you reduce quad overdraw. If we push it really far away, maybe we can cheat even more, just putting a picture of a tree in. I mean, does it really matter? If this is so far away that it's being caught in the distance fog, you can't tell anyway. But the better your cheating is, the closer you can do it before anybody cares. Take this simple cube. This picture kind of sucks, but we can make it better. Maybe by separating the diffuse from the normal. Now these can be lit nicely with some work. And we can go even further. Take a look at this technique from Ryan Brooks called octahedral impostors. The general idea is that you take that same tree and take snapshots from many different angles and use an octahedral mapping to get you a nice distribution of angles. Then with some blending, you can walk around the object and it kind of reacts like a real one. Now look at this thing. Even up close, it actually looks somewhat like the real thing, but it's all smoke and mirrors. You can scatter these out in the field now. They react to lighting, and at that point, you could even start playing with post effects like ambient occlusion or screen space shadows to make it look even better. One thing I should call out, be careful of both your average case and your worst case. If your average case is great, but every once in a while you turn the camera and hit 1 FPS, that's awful. As Jibrim kind of screamed this on Twitter, design your software to minimize fluctuations in performance. I'll give you an example. In a game, let's say you're wandering around the city, stuff is happening, blah blah, and then suddenly bombs go off, explosions, chaos. Let's focus on the particles in this case. Particles are expensive, they cause huge amounts of overdraw. So multiple explosions go off, you flood the screen with particles, and frame rate tanks. Except you can't tank the frame rate, that's not cool, you have to take this in stride. Well, you know roughly how fast you can draw particles, right? You've done your tests, speed of light, yada yada. On Prototype, back in 2005-2006, I did a dumb but surprisingly effective Hail Mary change. Moments before a big publisher demo, I put a hacky throttle on the effects. When all those explosions went off, we didn't just spawn everything. We pulled from a shared budget and damped how many particles each effect could actually use, scaling the density of effects. This evolved into a game of how do we distribute the particle budget. Closer, more important stuff, more budget. Further away things, less. 1 explosion or 100, things should stay even. Newer techniques are much smarter than that, doing things like dynamically adjusting the resolution, but the idea is just don't let the worst case be much different than your average case. So overall, that's kinda how optimization works. We started with our simple scene, unoptimized, and we worked through the various stages. We got the really low-hanging fruit out of the way, improved our input, and made sure to use the hardware's preferred way of drawing lots of stuff, and saw the scene's performance grow. After that, we got a bit smarter about distributing the work, culling out what was invisible, dividing the world spatially into regions to rapidly test, and again, we saw big improvements. Eventually, you hit diminishing returns because your hardware has real, verifiable limits, and that's when you start trying to get creative. What will people notice? What can I get away with doing? Do the same work, but better. Do less work, be smarter, cheat and lie. In reality, optimization work is a mixed bag of these approaches, but let's not nitpick. It's generally always that same approach. You figure out how much you want to spend on this, you profile and figure out where your problems are, find a problematic bit of code, make changes there, and profile again. The details will change as you get more experience, but let's not overcomplicate this. If you came into this video thinking I'd make you some sort of optimization monster in 20 minutes or however long this took, sorry. I've seen even experienced game devs, guys with a decade or more experience, blindly optimizing with no real plan, so just getting a good framework is a start. I don't pretend to be the best or to know everything. For any devs who have some interesting war stories of major performance improvements, comment section is below. Make sure to share. Cheers.